For today's seminar, we are very pleased to have William Slofstra from the University of Waterloo.
So thanks very much for having me. So I want to tell you about one of my favorite theorems. It's a theorem of Alex Arkhipov, and some work that Connor Paddock, Vincent Russo, Turner Silverthorne, and I have been doing to try and kind of figure out where this theorem comes from and can it be generalized. So the setting for this theorem is non-local games, and I apologize if you've seen me give a talk about this subject. You've probably seen this slide before. I think it's kind of mandatory to just say something for people who are just approaching the subject. So what is a non-local game? Well, it's a scenario where we have two players, Alice and Bob, and a referee gives them each an input, let's call it X and Y, and they each return an output, let's say A and B, to the referee, and the referee decides whether they win or lose based on the inputs they received and the outputs they gave. Now, the winning conditions are all known in advance, and Alice and Bob want to cooperate to win. They're on the same team. So the thing that makes this game actually difficult and interesting is that the game, the players cannot communicate while the game is in progress. So once the game starts, and before the players have received their inputs, they're kind of placed or locked in rooms where they can't send messages to each other. And thus, when Alice gets input X, she doesn't know what input Bob has received, and vice versa. And but she might have to pick what her output is supposed to be. Might depend on what input Bob got. So it can make the game challenging for the players to win. Now, what does a strategy for a non-local game look like? I'm going to jump right into some quantum mechanics here. So first of all, let's just say what data needs to be included to totally describe this game. It's such a simple scenario. We need very little data. So we just need to write down what the input and output sets are. These are finite sets. We need to say when the players win. So that can be given by a predicate function, which takes all four tuples of outputs and inputs to 0 or 1, with the interpretation that if VAB XY is equal to 1, that means the players, if they receive inputs XY and give outputs AB, then they win. And if the function is 0, that means they would lose on those inputs and outputs. And finally, this won't be so important for what I'm going to talk about today, but sometimes we want a probability distribution on the referee's, the questions the referee asks to be included. So a probability distribution on the possible, typo here, on the possible inputs to Alice and Bob. So it should be IA times IB. So if that's what a game is, what is a strategy for the players? Well, that consists of, in quantum mechanics, the players can share entanglement, and then they would make measurements based on the input they receive to determine what their output should be. So their strategy would consist of Hilbert spaces for each player, HA and HB, and then a set of measurements, say PXA on HA for every input to Alice, and a measurement QYB on HB for every input Y to Bob, and then an entangled quantum state that they share that's in the Hilbert space HA tensor HB. And the winning probability with this strategy would be the sum over X, Y, A, and B of the probability that that questions or inputs X and Y are given to the players times the predicate times the probability that the players answer A, B on inputs X and Y, which is, of course, this expectation, the bracket of PXA tensor QYB with psi. And the sum here is over all possible inputs and outputs. So the question we're interested in is, what is the optimal winning probability given a game? So maybe the motivation for this could even be practical, right? If we have some scenario where we think entanglement might be useful in practice, we might want to know, well, what's the best we can do with an entangled strategy? But really, you know, I want to ask this question on a mathematical level. We've got now kind of a practical question that can come up, and mathematically we want to know, is this a question we can solve? What are the best algorithms for it? And so on. It's nice, especially for the purposes of a talk, to turn this into a streamlined version. So rather than just asking what's the optimal winning probability, I'll just ask the decision problem: when is the optimal winning probability equal to 1? When can we play this game perfectly, in the sense of the players always win? So we've been getting more and more information about how hard it is to calculate these winning probabilities, and the answer has been it's not easy to calculate these winning probabilities, and in fact it's impossible. And the kind of most recent evidence we've got is a very strong form of that statement. So it's this MIP star equals RE result by G, Natarajan, Vidic, Wright, and Ewan, which says that it's undecidable to tell whether a non-local game has either optimal winning probability 1 or less than or equal to a half, given that one of the two is the case. So although we would like to know how to calculate this, unfortunately, it's not something we can calculate in theory, I guess I should say, rather than in practice. But it's not something we can calculate for general non-local games. So in this talk, although that's been really exciting news to get that result, and it's kind of really changed how we think about non-local games, you know, kind of learning that we can't really hope to calculate this value. In this talk, I want to kind of focus on the other side of that question, which is, if you know we can't do it in general, can we find families where we can tell if the value is equal to 1? I think it's worthwhile kind of looking for families of non-local games where that is the case, especially if it's something maybe way down the line. We are going to want to have maybe a kind of repertoire of games where we know, okay, in these situations, entanglement does work. We get an advantage with entanglement. Or we can exclude these. We don't get an advantage with entanglement on these games. So to kind of, so in this talk, I want to talk about a specific family of games with that property. And to say what that family of games is, let's start with an example of a game. So let's look at the Merman Pair's Magic Square. So I know a lot of you are probably familiar with this, but bear with me. So so this is a non-local game based around the following square with so it's 3x3 square with the entries labeled by x1 up to x9. I've also labeled the rows with a 1 and the columns with a -1. So the way this game works is that the players are given as input either a row or a column. And then if they're given, let's say, the first row, they have to output either plus or -1 for every variable in their row. So they have to output plus or -1 for x1, a plus or -1 for x2, and a plus or -1 for x3 if they were given the first row. And then to win, they have to satisfy, their outputs have to satisfy two conditions. First of all, the product of the outputs in their row or column must match the corresponding label. So for instance, if they were given row 1 and they outputted a -1 for x1 and a -1 for x2, they'd have to output 1 for x3 to have a chance of passing this condition, so that the product would be equal to 1. For columns, they have to get -1. And then the other condition, so that condition is just checked for each player individually. They have no problem satisfying that. But the thing that makes this game kind of a priori hard to win for the players is that their output must agree on any shared variables. So for instance, if Alice receives the first row and Bob receives the first column, then they must give the same assignment to x1. If they're both given the first row, then they have to give exactly the same outputs because they share x1, x2, and x3. So that's the game. When does this game have a perfect classical strategy? Well, notice that this is really can be thought of as a system of equations in the variables x1 up to x9. Although the values of the variables are either plus or -1, really that's just a way of writing a linear system over Z2 multiplicatively. So we can think about this as a linear system over Z2. It's got 9 variables, x1 up to x9, and 6 equations, 3 for the rows and 3 for the columns. And so a game, this game will have a perfect classical strategy if and only if there's a way to assign plus or -1 to each of the variables such that all the equations are satisfied. In other words, such that if it has a perfect classical strategy if the linear system has a solution. And it's easy to see that this linear system doesn't have a solution by a parity argument. If you sum up all the variables, you get the sum of the rows, which has to be 0 if I'm using sums. If I'm taking products, it would be 1. But the sum of all the variables is also equal to the sum of the columns, which would have to be 1 in Z2, or -1 if I'm multiplying things. Now, what about quantum strategies? Well, here we're in luck, because although we can't solve this system of linear equations over Z2 in the normal sense, we can solve it with operators. So it turns out there are observables, x1 up to x9, meaning just unitaries. So unitaries acting on a 4-dimensional Hilbert space in this case, such that, first of all, xi squared equals 1. So they're plus or minus 1 valued unitary observables. And second, the product across all rows is equal to the identity matrix. And third, the product across columns is equal to the minus the identity. And fourth, this fourth one is very important as well. If xi or xj belong to the same row or column, then they commute. So that means that we can jointly measure the observables if they belong to the same row or column. So to turn that into a strategy, what Alice and Bob can do is they can use those observables as measurements. So because condition 4, let's say if Alice gets row 1, she can use the observables x1, x2, and x3, and since they all commute, it's fine to treat them as a joint measurement. So the fact that this system has an operator solution implies that the quantum value is actually equal to 1, even though the classical value is less than 1. So I want to generalize this type of game. So let me describe a broader family of games called graph incidence games. So these games are based around graphs. We'll see how that connects to this square in a second. But rather than starting with a square, I want to start with a graph. And I want to start with a Z2 colored graph. That means I just assign an element of Z2 to each vertex. Doesn't have to be arbitrary, but it doesn't have to be a proper coloring is what I mean. We don't have to worry about adjacent vertices or anything like that. It's just an assignment of any function from vertices to Z2 counts as a Z2 coloring. And some notation that's quite handy here. Let's let E of V denote the edges incident to vertex V. So what is a graph incidence game of a Z2 colored graph G comma B? Well, in this game, the players receive vertices as inputs, let's say V and W, and then they have to output functions, which are assignments of plus or minus 1 to the edges incident to their given vertex. So one player would output a function from the edges incident to V to plus minus 1, and the other player outputs a function from edges incident to W to plus minus 1. And then to win, their outputs must satisfy, well, it's kind of the same thing we said for the magic square. The product of all their edges, of their assignments to the edges, has to be minus 1 to the label of the vertex. So that holds for both players. And second of all, their assignments must agree on all shared edges between the two vertices. So if E is in incident to V and W, then we have to have the output for E equal to the for Alice equal to the output for E for Bob. So here's an example. Let's use K33, and I'll indicate the vertex labeling just by the labels inside the vertices here. And so K33 is the complete bipartite graph on with 3 vertices in each partition, right? So we take 3 vertices and another 3 vertices and connect them in all possible ways. And then I'm going to label them by assigning 0 to all the vertices in the first partition and 1 to all the vertices in the second partition. So how would this game work? Well, each player is given a vertex. So let's say Alice is given the top left vertex. She would have to assign plus or minus 1 to each of E1, E2, and E3, such that the product of the assignments is equal to minus 1 to the 0, which is just 1. And if Bob is given the bottom left vertex, he would have to assign plus or minus 1 to E1, E4, and E7, such that the product of the assignments is minus 1 to the 1, because the vertex label is 1, minus 1. And then their assignments must agree on the shared edge, E1. So that's how graph incidence games work. Now, oh yeah, let me mention about the classical winning probability. So when is the classical winning probability equal to 1? Well, if and only if there's an assignment of plus or minus 1 to each edge, such that the product of assignments to each edge around each vertex is minus 1 to the vertex label. In other words, it satisfies the corresponding equation for that vertex. And as kind of a bit of a practice on this idea, it's nice to think through this fact. When G is a connected graph, this happens if and only if the parity of the coloring, which is the sum over BV for all vertices V in Z2. So if and only if this parity is even, or if and only if the sum is equal to 0. So how does that work? So this isn't an even parity coloring, so this won't have a winning, a classical winning probability 1. But let's say that we changed it so it did have even parity. Let's say we made this one. Oh, is my cursor showing up?
Yeah, it is. We can see your mouse icon.
Yeah, great. Okay. So let's say this, I changed this 1 to be a 0. So then it would be even parity because we'd have only 2 1s. What I could do is I could look at the path that connects the 2 1s and assign minus 1 to both of those edges and 1 to every other edge. So then the product around all the other vertices is just 1 because we've assigned 1 to all those edges. And at this vertex, we've got 2 minus 1s because we've got an incoming minus 1 and an outgoing minus 1. So that would give us a total product of 1 as well. And at each one of these, we have 1 incoming edge with minus 1. So we get minus 1 in each of these. And in general, what you can do is if you have an even number of vertices colored 1, you can pair them all up by paths, assuming the graph is connected, and figure out how to do your assignment based on that. Okay, so now let's go back to the Mermin-Paris magic square. Why is this a generalization of the Mermin-Paris magic square? Well, with K33, I've just been telling you about the Mermin-Paris magic square all along. Notice that in this square here, we have 3 rows and 3 columns, so corresponding to 3 vertices on the top and 3 vertices on the bottom. And then we've got x1 up to x9 corresponding to the 9 edges. And the key fact about the square that makes it K33 is that if we look at a row versus a column, they intersect in exactly 1 variable. And similarly, in K33, each top vertex and bottom vertex share exactly 1 edge. So this is exactly the same game. So graph incidence games in general, they're kind of a generalization of games like the Mermin-Paris magic square. Now, what can we say about, so for the Mermin-Paris magic square, having a perfect quantum strategy corresponded to having an operator solution to the corresponding equations. So what can we say about graph incidence games? Well, the exact same thing holds. So the quantum value is equal to 1 if and only if there are observables for each edge, which are plus or minus 1 valued, and such that the product of edges around, of observables assigned to each edge around a given vertex is equal to minus 1 or minus identity to the vertex label. And finally, such that if 2 edges are incident to a common vertex, then the corresponding observables commute. So this theorem, in a more general form, dates back to a paper of Cleve and Mittal. So they actually show that a theorem like this holds for what are called constraint system games. So it's quite general. Now, I think I put groups in the title of this talk, and I want to do some group theory. So I want to rephrase this theorem that I just mentioned in terms of groups, in fact. So the key fact in this theorem is that all these relations just involve multiplication. So it's kind of prime for restatement in terms of groups. So what I can do is I can look at the finitely presented groups generated by the edges. So the only thing that's wrong with these relations that doesn't really fit into the framework of groups is that we've got a minus 1 here. We can't really talk about things like -1 inside groups. Maybe I should also mention just a little bit about, so I'm going to start throwing some kind of jargon about group theory around. In particular, I'm going to start talking about finitely presented groups. And maybe I better say a little bit about what those are just in 30 seconds. So the idea is a finitely presented group is it's an algebraic object where we start with some set of generators. We can call them anything we want. And then we just put down some relations that the generators have to satisfy. And we can put down any relations that we want. And then we can just manipulate the generators according to the relations and see what we get. Sometimes if we put down relations that are too constrictive, everything will end up being equal to the identity. But if we put down some nice relations, we can end up with very interesting algebraic objects. So what I want to write down here is the group generated by the edges. So I'll call the generator corresponding to the edge XE. And I want a generator J for to correspond to -1, because I can't really talk about -1 inside a group. That's the only kind of limitation to it. And then I want to add relations which say, first of all, that J commutes with every other generator. We say that J is central. And J squares to the identity, just like -1 does. And second, I want to just add the relations that correspond to exactly the relations we had here, 1, 2, and 3. So I want to say that every generator squares to the identity, that the product around every vertex is equal to, rather than -1, J to the vertex label. And finally, that any two observables for edges which are incident to a common vertex commute. And then we can rephrase this theorem of Cleave and Mittal to say that the winning probability for this graph incidence game is equal to 1 if and only if the element J is not equal to 1 in this game. Or in other words, just to be clear about what that means, so J is not equal to 1 in this group if and only if there's no way of showing J is equal to 1 by applying these relations repeatedly.
So you probably already mentioned this, but just to clarify, so we're talking about possibly infinite dimensional strategies here?
Yeah, although actually I want to sweep that all under the rug for this talk, even though those things can be really interesting for other classes of games. For graph incidence games, they're not interesting. So there'll be a perfect finite dimensional strategy if and only if there's a perfect infinite dimensional strategy. So then I'm just going to pretend they're the same thing basically for this talk.
Oh, okay. Oh, yeah.
Yeah,
Okay. So
cheat a little bit.
Yeah.
The only exception to that is actually right now I'm going to mention linear system games. So if you've learned about linear systems games before, this is all going to look very familiar, because this is actually just a special case of what happens for linear system games. So I'll get back to that in a second, actually. Sorry, that's not right now. In one more slide, I'll get back to linear system games. But before I get into that, I want to say what Arkhipov's theorem is, because that's the whole point of this talk. And I don't want to leave you hanging too long on what Arkhipov's theorem is. So let me remind you of the summary so far. We have a group theory characterization of when we have a perfect quantum strategy in a graph incidence game. So the game has a perfect quantum strategy if and only if this element J is not equal to the identity in the corresponding graph incidence group. And as for classical winning probabilities, if G is connected, we can say that the classical winning probability is 1 if and only if B has even parity. So it would be nice to have a characterization like B for part A. Part A seems needlessly complicated compared to B. And so this theorem that I really like, due to Alex Arkhipov, is that if G is connected and B is odd parity, so B doesn't hold, there is no classical winning, the classical winning probability is less than 1, then the quantum winning probability is equal to 1 if and only if G is non-planar. Now, to say a little bit about why I like this theorem so much, let me first go back to this linear system games. So as I mentioned, graph incidence games are a special case of linear system games. So basically, just like we said, if we've got a graph with a Z2 coloring, we can turn it into a game. If we have a linear system AX equals B over Z2, we can turn that into a game. If we take the matrix A, so leave B as the coloring of a graph and take A to be the incidence matrix of the graph, then the game we get from this linear system game is the graph incidence game. So this is So graph incidence games are a special case of this construction. This theorem that I mentioned in group theory holds for linear system games as well. But unfortunately, this theorem of Arkhipov breaks in the strongest possible way for general linear system games. In particular, it's undecidable to tell if this element j is equal to 1 in this solution group. And in general, it's hard to say anything about this group that's really definite. If we want to test whether particular generators are equal to the identity or whether certain identities hold between the generators, all of those things will be undecidable. So, from the point of view of linear system games, these groups are very intractable objects. So with that in mind, Arkhipov theorem is quite remarkable because you can test whether a graph is planar in linear time, I believe. So it gives you a very fast way of telling whether or not you have a perfect quantum strategy for graph incidence games. And the other remarkable thing about it, which doesn't come from its connection to linear system game, is the fact that it turns out to be equivalent to non-planarity. First of all, it's really nice that it's something that's so well studied. And second of all, it's kind of, you'd think, well, if a theorem like this was going to work, it would be if and only if G is planar. That's usually how such theorems go. Why is it non-planar? It seems a little, it seems backwards. So looking at this theorem, I think you just kind of get drawn in and want to know, where is this theorem coming from? Obviously it comes from Alex and the proof of the theorem, but is it part of some more general set of ideas? And in particular, can we understand more about these groups in the case of graph incidence games? Can we apply the same ideas to understand other properties of the group? So that's what I want to kind of talk about in this talk. And to explain where we might look for to try, where can we go to try and generalize this theorem of Arkhipov? Well, the answer is we should look at the theory of graph minors. So I'll remind you of what those are. So remember, a graph H is a minor of a graph G. And we use the notation H is less than or equal to G if it can be constructed from G using the following operations. So one operation is vertex deletion. So in vertex deletion, I'm going to actually put up some graphs in a second where I'll show some examples of these, but I'll just mention them verbally now. So vertex deletion is you take a vertex in your graph G and you just delete that vertex and all the adjacent edges. Edge deletion is an operation where you pick an edge and just delete that edge. You leave the incident vertices unchanged, aside from deleting that edge. And edge contraction is the tricky one. You take an edge and then you kind of squish the two vertices together along that edge. So you end up deleting the given edge, but you identify the two endpoints of the vertex. So Wagner's theorem states that G is planar if and only if K33 and K5 are not minors of G. So that's probably the place most people encounter this notion of graph minor. You might be wondering, why is this? So one thing you might be wondering looking at this list, this doesn't match the graph minors that I know. And second of all, why is it called Wagner's theorem and not Kuratowski's theorem? So there's two versions of this theorem and two notions of graph minors, actually. This is the algebraic minors, and the other one is the topological graph minors. Amazingly, they give the same graphs for the forbidden minors here, but they're kind of two theorems from the same period of time. So now this is really interesting when you look at this theorem, because these are the minors that characterize when we have a perfect quantum strategy, and these are also kind of the most famous cases of graph incidence games. K33 is the magic square game, and K5 is the magic pentagram game. So looking at this, you know that Arkhipov theorem must have some connection with graph minors. That's inevitable. But before I can say what that connection is, we need to say, because Arkhipov theorem involves Z2 colored graphs, so we need to modify this picture a little bit to say what are graph minors for Z2 colored graphs. So this gives me a chance to actually give you the pictures for graph minors here. So the one rule of Z2 colored graph minors is that we don't want the parity of the coloring to change when we apply the graph minor operations. So other than that, let's just do the normal minor operations. So I can delete a vertex. That's fine. You just delete the vertex and delete all the incident edges. The only problem is if we delete a vertex which is colored by 1, then the parity of the coloring will change. So let's make a rule. We're only allowed to delete vertices which are colored by a 0. So that's the only change to vertex deletion. Edge deletion is really easy because it doesn't involve the coloring at all. You just delete the edge and leave the colors all the same. So we can just keep that unchanged. And in edge contraction, we have to take these two vertices. So this is how edge contraction works. You take, let's say we want to contract this edge D. We would squish these two endpoints together and leave all the other edges kind of unchanged. So we get one vertex which shares all the previous edges. So in this one, we kind of get rid of the two old vertices and make a new vertex. And we have to say what the color of this new vertex is. And the answer is we just take the colors of the input vertices and add them together, mod 2. So if you had a vertex 1 and vertex colored by 1, you would get a vertex colored by 0. If it was 1, 0, you would get 1 instead. So it's a pretty natural operation for colored graphs. Now, the only thing about this, the graph minor operation so far, they're great, but it's really annoying we can't delete vertices that are colored by 1. It seems to restrict us from deleting a whole bunch of vertices. So it would be nice if we could shift the vertex labels around. So we add one new operation. I call it edge toggle. I'm not sure if it's a good name or not. But the idea is you select an edge, in this case, let's say D, and you just add 1 mod 2 to the endpoints of that edge. So because you're adding plus 1 to 2 vertices, it leaves the parity of B unchanged. But let's say I wanted to delete this vertex, which is labeled by 1. If I toggle it, then it'll be labeled by 0, and I could delete it after I did the toggle. So it gives us a lot more options for doing graph minor operations. Okay, now, although I think those are kind of natural, looking at that, you should say, well, they just kind of wrote down some graph minor operations. Why are those the right graph minor operations? Actually, they're not. I'll get to a technical point about what the argument against those being the natural minor operations in a second. Let me say the positive evidence. So with this notion of graph minor operations, we can actually take any graph minor operation. Let's say it goes from a Z2 color graph G comma B to another Z2 color graph G prime comma B prime. We can map that to a surjective group homomorphism from this graph incidence group of GB to the graph incidence group of G prime B prime. And to prove that, you just go through the list of minor operations that I said and write down what the homomorphism is in each case. So let me tell you what it is for edge deletion, because that's kind of the easiest operation. Now I know this whole group presentation stuff is just kind of sudden if you haven't seen it before, but you should think about it, as a pretty natural object. Let's go back and look at the graph for edge deletion. All the group is it's just an algebraic object where we have a generator for each edge, and we've got some relations that, the most important one is that the product of edges around each vertex is equal to either the identity or equal to J. So what happens if we delete an edge to our relations? Well, we've removed that generator from the equations for the endpoint vertices, which is basically just like setting that generator equal to the identity. So that generator no longer appears in the group anymore either. So what we can do is we can just observe that actually the graph incidence group of G prime B prime, if this is the result of deleting an edge E from G, it's actually the graph incidence group of G comma B mod the relation that sets this generator equal to the identity. So we take the normal subgroup generated by this generator and quotient out by that. So for our surjective group homomorphism, we can just take the quotient morphism from this first group to this the second group. So the end result of that is that if we have a Z2 colored minor of a graph of a Z2 colored graph G comma B, then there's a surjective group homomorphism between their graph incidence groups. And an important technical point, we'll see why in a second, out of this is that the special element J that represents -1 is preserved under this group homomorphism. So the J for this first group is sent to the J for this second group. We can see that in the one example I mentioned here, where we didn't do anything at all to the J. We just changed this generator XE. Okay, so why is this useful? Well, we say that a property of graphs is minor closed if whenever H is a minor of G and G has the property P, then H also has P. And I think this is one of the most important theorems of the 20th century. It's the Robertson Seymour theorem. It states that if P is a minor closed property, then there is a finite set of graphs. It's amazing that we always get a finite set here. It's obvious if the theorem's tautological if you put in infinite. But if, so the whole content of the theorem is this finite part here. There's a finite set of graphs such that a graph G has P if and only if it does not contain any of the elements of F as minors. So the set F is called a set of forbidden minors for this property P. So we've already looked at one example of a minor closed property. Planarity is a minor closed property. And the forbidden minors for that are K33 and K5. But in general, you get a set of minors like this. It could be a very different list of graphs. The theorem doesn't say anything at all about what the graphs actually are. It just says they have to exist. But they exist for any minor closed property. Now, we've got a lemma that connects graphs under the graph minor operations to finitely presented groups. So we should try and figure out what the analog of minor closed properties for groups are. We need to involve this element J in the same way that we involve colorings in our graphs. So let's say that a group over Z2 is a pair of G and an element J. So G is just a group, and J is some element of G that squares to the identity. Oh, excuse me. Usually I make this definition requiring this to be a central element, although I suppose it doesn't really matter. It's not considered, this is supposed to be kind of a lightweight definition. So, and we define a morphism of groups over Z2 to be just a group homomorphism between the corresponding groups, which sends the element J of the first group to the element J of the second group. And finally, we say that a property of groups over Z2 is quotient closed if whenever we have a surjective homomorphism from G to H, sending J to J, if the first group has the property, then so does the second group. So many properties of groups are quotient closed. Like for instance, if you have a surjective homomorphism from G to H and G is trivial, then H has to be trivial. Or if G is finite, then H has to be finite. Or if G is cyclic or abelian or amenable, then H has to be the same, cyclic or abelian or amenable in turn. And the same thing, well, it's actually a little harder to come up with natural properties of groups over Z2. So I should say any property of groups is also a property of groups over Z2. You just ignore the J element. And any quotient closed property of groups is a quotient closed property of groups over Z2. But there is one, very relevant to us property of groups over Z2. So having J equal to 0 is a quotient closed property of groups over Z2, right? If we have a surjective homomorphism, it doesn't matter that it's surjective. If we just have a homomorphism from a group over Z2 to another one, and we know that the first group has J equal to the identity, well, group homomorphisms send the identity to the identity. So if JG goes to JH, then JH also has to be the identity. So this is a quotient closed property as well. So what can we do with our lemma? Well, it gives the following corollary. If we have a quotient closed property of groups over Z2, then there is a finite set of Z2 colored graphs. So this is a corollary of this pretty easy lemma and the very difficult Robertson Seymour theorem. So, right, so that's where this finite set comes from. So there's a finite set of Z2 colored graphs such that when G is connected, the group has this quotient closed property P, if and only if our Z2 colored graph does not contain all the elements of this finite set F as minors. Now you'll notice that I snuck the word connected in here, and there's a technical problem that requires us to stick connected in here. That this is where you kind of wonder, did we really get the right list of minors or not? So normally I would just kind of say, well, let's just move on. But actually, it's kind of an interesting one. It's kind of funny because we're not allowed to delete vertices that are labeled by 1. If we just take a graph with lots of vertices all labeled by 1 and no edges, then that graph technically has no minors. There's nothing we can do to that graph. Normally, we'd have like the single vertex graph as a minor, just go down to like one vertex. But with this setup, we can't do that. So we've tinkered with this a little bit, and figured out that if we add some additional operations, for which the lemma also holds, actually you only need to add the a natural operation you can add is that if you have two connected components which have exactly the same coloring, then you can collapse it to one connected component. Then you can get a version of graph minors where the corresponding version of this corollary, holds for, it doesn't hold for all graphs, but whether or not it holds for all graphs is equivalent to what we believe to be an open problem about kind of the well-quasi-orderedness of graph minor properties. So it really kind of gets into the weeds a little bit, and maybe the lesson learned out of that is that it's not so bad to restrict to connected graphs here and just kind of not worry about this technical problem. But yeah, there's kind of some interesting things going on there that are still unresolved. The reason it's easy for connected graphs is the following: that if you have two connected graphs, then because we added this edge toggle operation in, we have that one of them is a minor of the other if and only if H is a minor of G in the normal sense and B prime and B have the same parity. So really, the coloring only enters with the in the parity as far as the minor relation is concerned. Okay, so we have this corollary, and we know that J equal to 1 is a quotient closed property. So the corollary implies that that this property can be characterized by a finite list of forbidden minors. And so we should see, so in some sense, if we knew this corollary ahead of knowing Arkhipov theorem, we'd say, oh, okay, so there must be some finite list of forbidden minors that characterizes this property. I wonder what they are. This corollary doesn't tell us what the list of minors is, but let's see what they are. So this is just restating Arkhipov theorem, because that theorem tells us when J is equal to 1. So it says for connected graph, J is equal to 1 if and only if the graph G comma B does not contain the following minors: K33 odd, that means with any odd color parity coloring, K5 odd, and C1 even. C1 is, I just mean the graph with a single vertex. So the reason this is in the list, if you contain C1 even, then you have to have an even parity coloring, which means that you have a classical perfect strategy, which implies that J is not equal to 1. Actually, it implies there's a one-dimensional representation where you can show that. So this minor takes care of the kind of the classical case or the even parity case. So it's nice that we can kind of state that all in a uniform way. By the way, Carl, do you want to go right to the hour or stop at 50 minutes?
Right to the hour is fine.
Yeah, okay. Now, so it's nice that this corollary allows us to anticipate this theorem, but I wouldn't go so far as to claim that just because we know that there's some list of minors that we really explain this theorem. To explain this theorem, we need to know why we get these minors in particular. So I want to ask the question, does knowing this lemma help us actually figure out what the minors are? And, in some sense, yes. So here's how we would prove Arkhipov theorem in this language. First of all, we would determine the graph incidence groups for these three Z2 colored graphs. And what we'd find is that in each case, they're all finite groups with this J element not equal to 1. So what that means is that if you have a graph, let's say a Z2 colored graph G comma B, and one of these three is a minor of that graph, by our lemma, there's a surjective group homomorphism from gamma GB to gamma H comma B prime, sending J of the first group to J of the second group. And we know that J is not equal to 1 in this second group here, because that's what we found in our calculation. So it has to hold that if you contain one of these as minors, then you have to have J not equal to 1 in G comma B. Now, so that explains that if you let's see, which way is that? That's if you contain one of these as minors, then you can't have j equal to 1. So in the other direction, we need to show that if you contain one of these as minors, sorry, if you don't contain any of these as minors, then you have j equal to 1. And for that, there's actually a natural way. I'd love to talk about that, but something kind of had to be cut out of this talk. So I'm just going to say it in a couple of lines. But there's something very natural going on there as well that explains exactly why planarity comes in. And that is that, that relations in groups over Z2 are captured by Z2 colored planar diagrams called pictures. If we scratch out the over Z2 part, then this is it's a very old kind of well-known fact that goes back to Van Kampen in the 1930s. So, so this is a very kind of planar diagrams are a very natural way of thinking about the relations that hold in groups. And if we know that B is odd, and if we don't contain, if we're connected and don't contain C1 even as a minor, then we have to have B has to be an odd parity coloring. So if B is odd, then it turns out that if G comma B has a planar drawing, then that planar drawing is actually a picture showing that J is equal to 1. So the graph itself is the picture that you would use to show this fact. So that's all I'm going to say about that. But you know, in a Blackboard talk, this is, you know, kind of where you could just cut loose at this point, drawing lots of pictures and stuff. So you know, maybe if you're interested in this, ask me at some point when we have a Blackboard in front of us, and I'll be happy to oblige. Now, so hopefully this helps kind of explain. I think that Arkhipov theorem is kind of very natural in this group/graph theoretic world where we have graphs mapping to groups. But really, if we've got something here, the question should be, are there, you know, can we actually extend Arkhipov theorem? Can we characterize other properties in the same way? We're supposed to be able to find minors for any quotient closed property of groups over Z2. So, and I said there were lots of quotient closed properties of groups. So can we find the minors for those properties? And so far we've been able to find the minors for 2 properties. And really this is kind of a setup for life really here. You can just write down a quotient closed property and start working on what the forbidden minors are of it. So maybe you can invite me back next year and I'll give you the update on what the minors are for something else. But here's what we can prove right now. We can show that the graph incidence group is finite if and only if G avoids, so C2, this refers to the disjoint union of two cycles. Okay, so if and only if G avoids the disjoint union of two cycles and K36, and the group is abelian if and only if it avoids so the following graphs, so K33 with an odd parity coloring, K5 with an odd parity coloring, K34 with an even parity coloring, and again, 2 disjoint cycles with any parity coloring. The reason I dropped the coloring out of the first one is actually whether or not this group is finite is totally independent of the color. So it turns out we don't need to bring Z2 colored minors into this at all. So I want to say a little bit about why we can find these minors based on our lemma here. So the idea is, once again, we want to just kind of analyze the groups we get by looking at these forbidden minors. And what we notice right away is that for 2 disjoint cycles, this group is actually the free product of Z2 with Z2, which it doesn't matter if you know what this group is or not. It's a group which is both infinite and non-abelian. It means if you contain this as a minor, you're not going to be finite or abelian. And notice to say that a graph contains this as a minor, that happens if and only if G contains 2 disjoint cycles. So when we say that a group avoids this graph, we're saying it doesn't contain 2 disjoint cycles. Every pair of cycles has to intersect in some vertex. So it turns out there's a very nice characterization of graphs that do not contain 2 disjoint cycles due to Lovash. any such graph has to fall into one of the following categories. It either has to be a forest plus a vertex, where we add, like we can add arbitrary many vertices to that extra vertex. Sorry, arbitrary edges to that extra vertex. Or it has to be a wheel graph. You can kind of see the common pattern here. Like in the wheel graph, every cycle has to go through the, so wheel graph is like a cycle with a vertex in the middle that connects to all other vertices. Every cycle except the outside cycle on a wheel graph has to go through that middle vertex. So that means that any two cycles either share that middle vertex or share some outside edge. So K5 also has this property. And finally, if you take K3n and add, I've screwed this up here. It should be edges added arbitrarily to the first partition, the one with 3 vertices. What will happen there is that any pair of cycles, since it's a bipartite, well, kind of a bipartite graph, any pair of cycles has to have at least 2 vertices from the first 3 vertices, and so must overlap. And so actually all of these cases, A, B, and C, are then easy to analyze. D is the interesting case. As you can see in the theorem, we get K34 showing up and K36 showing up. Now, I'm going to say really briefly, since I got, I guess, 3 minutes left, why we care about the finiteness of this group. So I've kind of presented this as just, here are some properties of the group. Let's just see if we can find the minors. Of course, that's a really fun mindset to be in, but what relevance does this have to quantum information? Well, there is actually a reason to care about the finiteness of this group. So maybe I'll just kind of go through this pretty quickly. So we say that a non-local game is a robust self-test if, first of all, if there's some optimal strategy and some function f, such that then for every near optimal strategy, there are local isometries such that applying those local isometries moves this near optimal strategy to be kind of equal to or nearby with the ideal strategy. Tensor some junk state. And this function f is there to kind of quantify how nearby the strategy is, depending on epsilon, how close we are to optimal. So self-testing, of course, has been a pretty popular subject in the last few years. There's been a string of results. So I mentioned the fact that CHSH is a robust self-test. Magic square is known to be a robust self-test. Magic pentagram is known to be a robust self-test. And these two in particular are kind of unified by this result by Coladangelo and Stark that says that if you have a linear system game and the solution group of that is finite and has a unique irreducible representation with j going to -1, then this linear system game is a robust self-test. And the magic square and magic pentagram games both satisfy these conditions.
And that doesn't need to be a graph theoretic, a linear system game. It can be arbitrary.
Yeah, that's an arbitrary linear system game.
Oh.
Yeah. So now a key part of self-testing is that there is kind of it says an optimal strategy here, but it's kind of the optimal strategy because every other one has to be close to that. But actually, in this theorem of Coladangelo and Stark, there's really no reason to have this unique irreducible representation. The key part is really just that the group here is finite. So I'll say a little bit about what happens if you drop the uniqueness part here. So this theorem is kind of an assemblage of stuff that a lot of people know, I think. So I've just said after Coladangelo and Stark, although maybe it involves a bunch of other ingredients as well. Suppose that you have a finite, so I've stated this for graph incidence games, but this is for general linear system games as well. But I'm going to apply it in a second to graph incidence games. So suppose you have a graph where this graph incidence group is finite, and it actually has a perfect quantum strategy. And let's say, so the thing about finite groups is that their group algebra splits into a direct sum of irreducible representations. And in some of those irreducible representations, j will be equal to -1. In some, it'll be equal to 1. So let's take the irreducible representations where j is equal to -1. So first of all, every one of these irreps can be turned into a perfect strategy for the game. It uses a maximally entangled state on the tensor product of the two Hilbert spaces. Second, all other perfect strategies are weighted direct sums of these irreducible strategies. That means you want to take a state where you use each one of these states with some weight. And finally, so the game is a robust self-test in the sense that if you have an epsilon, like a near optimal strategy, then there are local isometries that make this this near optimal strategy close to one of the strategies in part B. So in particular, rather than saying, so remember in this definition, we could say that if you just set these equal to the identity here, you would get that the state is close to the ideal state. Here, you could say that the state is close to some weighted sum of some kind of irreducible ideal states, rather than actually equal to kind of a unique ideal state. And so in our theorem here, we had that this group is finite if and only if this avoids two disjoint cycles and K36. So in particular, K34, and we already know about K33, it has this unique ideal strategy. But K34 and K35 are finite and don't have unique ideal strategies. Actually, in this case, you can just plug these things into a computer. You'll find that this group for K34 has 16 irreps with j equal to -1, all of dimension 4. So this would be an example of a robust self-test where the ideal strategies are weighted direct sums of up to 16, well, of 16 irreducible strategies. It's kind of very interesting self-testing property. And I should mention that games with similar non-unique self-testing features have been found by others, Coladangelo, Mehta, Musavi, and Javi, and by Kaniewski. So I'll finish there.
Great, thank you.